Well, hi there. I'm gonna show you this little program I recently made. As you can see, this program solves the displacement for this sculpture that is under some forces. It uses finite elements in shape of tetrahedrons, and well, basically, um, you can see the intensity of the color means like the displacement of each node. The more color, the more displacement. And this displacement is scaled by a factor of 100. I'm gonna go down to some of the theory behind this and about the code I used. So yeah, let's start. Well, first of all the pre-processing is done in ANSYS. I use ANSYS because I already knew how to use it. This you can see here the same model that I use prisms and cubes and everything, and I just then mess everything with tetrahedrons. And here with these commands, you can see I can plot the nodes, the elements, and so on, and the material properties, constrain the nodes, the forces applied on the nodes, and then later on I can load all those files in my program. This is in this folder. There are all the forces, displacements, and so on, and a scale factor that changes in time for the animation. That's what you can see there. And well, that's it. It's all the pre-processing and making the geometry and so on. And now, how does the program really work? Well, for that, well, this could be in 2D. What we always want to find is, like, we've got a system with an stiffness matrix K multiplied by the displacements of the nodes, gives you the force acting on the nodes of those elements. And our objective is always to find the value of the K matrix. Well, in the case of a tetrahedron, we may have our polyhedron here, our element with its coordinates and so on, and we may want to know the displacement of at any middle point in the element. This is all needed to get the stiffness matrix. And well, for that we may want to use a shape function which takes the displacements in any middle node in terms of the displacement of the corners of the nodes of this element. It will be the shape of our shape function, which will be in this case 3 by 12 matrix, and this the displacement is again a vector of 12 elements. The expression for our stiffness matrix is this, the integrate of B transpose multiplied by D and by B again. B is like the derivative of our shape function, and because of this is 3D, the derivative, to apply the derivative we have to use all these matrix that applies onto the n, which has the shape functions. These three are the main stress directions, and those are for the like shear forces or stress that go in the element. So the solution for that would be a 6 by 12 again matrix. And here in the code, this is a piece of the code where I just get solve the B matrix. This would be one cell, and you can see the matrix is pretty long. I use a script for mm, print all these values, so basically to print the C code for that. And as you can see, then we have to multiply the B matrix we just found by D. This is like another function, in this case 3 by 3, and in terms of the Young modulus and the Poisson modulus for any given material. And to compute this integral, we just see that in this case of a tetrahedron n can be expressed in terms of x, y, z, and then the coordinates of the element. And this is all linear, x, y, z terms. So when we derivate this function to get b, we only get the scalars. I mean, all you can see here is the scalars, the coordinates of the elements, but not x, y, or z alone. So to compute that integral, you can just multiply everything by the volume of the element. So in here, this is expression of just the K matrix, which is what we may find down here. Multiplication of those three matrices is done in there together with multiplying by the volume. And well, that's it. Then what would you want to do with your K, local stiffness matrix of the element? You may want to build the global stiffness matrix. That is done doing an assembly of this matrix. Well, in 1D, just to make the comparison, the local stiffness matrix for a spring, for example, looks like this. But in a more general case, we would have, this is number of nodes of the element, in our case 4 in a tetrahedron, 4 submatrices, each one, this is end of number of degrees of freedom, 3 by 3 matrices, each of these submatrices. So in our case, we would have a 4 by 4 submatrices in our tetrahedron local stiffness matrix, on the whole a 12 by 12 matrix. And in the assembly of this, we would have to put all these 16 submatrices scattered around. This is done in a particular way according to the element, to the nodes it connects. Basically, the width done is so that all the elements uh, are under equilibrium, as well as all the nodes. That is what we have to apply just to see how this would be assembled. And well, in my code, as you can see, it's one of our elements in here. In its P matrix and local stiffness matrix can be calculated independently one from another. Okay, so what I just use in my code is CUDA, which is like an extension of the C language that lets you program on the graphics card and lets you do some things in parallel. So what I basically do is build all the elements local stiffness matrix at the same time and assembly them in the global K matrix. But as you can see, if we've got like any particular location where two nodes, a node where two elements connect, we if we launch parallel functions like that, we may have a collision of two functions writing down on the same cell. So what I just do is find the groups of elements that do not share any node and find their local stiffness matrix and assembly those at the same time, and then for the other next of groups that do not share any element, any nodes, and so on until the end, where I would have all the global key matrix. And that's why be met. This is the function that does all these. As you can see, all these arguments between elements are this is not standard C. This is what CUDA uses to specify what we are launching in parallel, or how we are doing that. And that basically does what I just explained, doing all these things in parallel, and then the other group and so on. That's why all these things goes in a loop. And that's all in the loop. And then, well, little more, then you just have to apply in this loop the boundary conditions for the global key matrix, and that's it. Then you just all you're left is just solving the system. So how you would do that? Yes, well, I just to solve the system, I use audio decomposition to solve this system. You can use Cholesky because K is gonna be always symmetric, but I wanted to reuse the code to be able to solve any kind of system even if the given matrix was not symmetric. So I use LU, the composition, which you can see decomposes the matrix in a lower and upper matrix and easily lets you solve your matrix, your system. Well, I also parallelize this in CUDA. Well, I'm not going to go much in detail, but I this would be our global key matrix, which in this example is got like 1000 nodes. 1000 nodes by the degree of freedom, which is 3. This gives us a 3000 by 3000 matrix. And then I go to several steps. Well, I use a blockwise decomposition, not standard LU. And then, well, this is made of several steps, and steps need some more sub-steps and so on. And again, I use CUDA with blocks and threads. Yeah, well, yes, I'm giving you an idea that this can be also highly parallelized, and just to save time. This is, well, you can have a look at this. This is where the call to the LU decomposition is done, and that function is like no, read this in here. This is the call, and this is the main of a first loop, like to make these stages, and then several phrases again with CUDA launches like threads and so on. And well, in the end, that gives back to this function the solution, the displacement, which is u in here. Displacement. Now all that is left is just plotting using, the graphics part. Well, just for the window thing, I use SDL for the window management. can also go under, as you can see, you can put in commands and so on, and you can see here, just put the command and it prints data wherever. And then for the graphics I use OpenGL, and for the color, to just to draw the color transition in its triangle, I use NVIDIA C shader, you know. And well, basically that's a brief review of how this works. It looks like a cream caramel on an earthquake or something. So well, that's it. Thanks for watching, and I know, post. Feel free to post any comment.